All right, we're trying this recorded lecture thing again. I threw together a PowerPoint for the Star Wars problem. I thought that was a good example of two-dimensional physics using some trigonometry, making a triangle to solve a problem from a Star Wars scene. So, the first part of this problem, um, basically what has happened in this scene is the Empire is trying to catch the Millennium Falcon and Han Solo and all those guys, and Han Solo has evaded them by going into an asteroid field. So the giant ships chase them into an asteroid field, and of course, one of the asteroids hits the giant ship called a Star Destroyer, and it smashes into it. So there's a lot of forces involved in that collision. All the numbers are there. I don't need to read them to you. The first part of this, you see that we need to figure out the acceleration of the asteroid. So the overall goal is to figure out how fast is the acceleration of the Star Destroyer backwards. So how quickly does that Star Destroyer begin moving to the right? I don't really like that color. Let's try this one. And no color is really going to show up nicely there. Ooh, okay. So the Star Destroyer is moving to the right. That way we need to figure out the acceleration. That's the long-term goal. But the first portion of this problem is just to figure out the acceleration or deceleration, I guess, because it's slowing down of the asteroid. So the asteroid begins at 102 meters per second. It ends up at 0 meters per second. So we're going to say it transfers all of its kinetic energy, all of its momentum into the ship, and then it stops. So it was coming in at 102. After the collision, it stops. We need to figure out what was that um, what was that acceleration. So yeah, like it says, we need the acceleration. So the equation it gave us for acceleration, which we already remember from way back in our kinematics unit, is that the acceleration is the time derivative of velocity. How quickly is velocity changing with time? So just the change in velocity over time. I think I may have said acceleration there. So let me take a step back. Acceleration is the change in velocity over time. So basically, how quickly is your speed changing, taking into account direction. So our asteroid's final speed, final velocity is 0. Its original velocity was 102. So we plug that into the delta V portion of the equation, and that change took 0.07 seconds. So that's what we divide by. And there's our answer, negative 1,457 meters per second squared. So very, very quick deceleration, which you imagine would probably come with a pretty large force. So it's a pretty heavy object. It's a big asteroid. It's slowed down very, very quickly. You would guess that takes quite a bit of force, which we're going to calculate in the next step. So one last thing, actually, this was the acceleration of the asteroid. So how quickly the asteroid is slowing down, not of the spaceship. So the thing that was slowing down from 102 to 0, that was the asteroid. And it sends the spaceship backwards a little bit. So you want to make sure you note that this was the acceleration of the asteroid. we do not yet know the acceleration of the spaceship. Okay, so now we need to calculate the total force between the asteroid and the Star Destroyer. So that's going to require using Newton's second law, force equals mass times acceleration, in order to calculate the total force. And this is going to be at an angle, at that 50-degree angle. We haven't done any sines or cosines yet, so it's not x or y force, it's just total force at an angle using F equals ma. So from the last portion, we know that the acceleration of the asteroid is that 1,457 meters per second squared in the negative direction, or I mean, positive and negative doesn't really matter right now because we're at some random direction, right? We're at 50 degrees. We're not in X or Y. So the negative's arbitrary. We're just looking at total amounts right now. I put the negative in there anyway, just because that's what the math made it look like it should be, but it doesn't really mean anything. So we need to use Newton's second law, F equals ma. Since the acceleration we're using is that of the asteroid, we also want to use the mass of the asteroid, keep it consistent. We can't take the asteroid's acceleration and then plug in the mass of the ship. Those are two different objects. They need their own separate equations. The object we're doing calculations for right now is the asteroid. That's the acceleration we have, so we need to use that mass. So plug in the numbers, and there is our force. So then let's look at the free body diagrams here. We've got the asteroid on the left, ship on the right. These are a Newton's third law pair. So the force that the ship feels from the asteroid is going to be the opposite and equal force that the asteroid feels from the ship. These two forces are going to be equal. Therefore, both of these forces are going to be that 1,491,968 newtons. If you want to round it to an easier number with a few zeros at the end, that's perfectly fine. We're not keeping track of significant figures, but about 1.5 million newtons worth of force here during that collision is what the calculations end up giving us. Okay, so now it's time to use our new knowledge of trigonometry to look at the sines and cosines of the situation. We have this angled force, 50 degrees. We need to turn that into just x. X direction is what we're interested in. That was the goal from the problem way back at the beginning, is to figure out the x direction acceleration of the ship. How quickly does the ship start going backwards from this collision? So we need to figure out, how do we get the x direction here from this 50-degree angle? So the triangle is kind of represented there. If you look up at the top, up here, you can see that the collision triangle is represented in the diagram there, which is really helpful. And then down below in the workspace, that collision triangle again has been represented so we can easily see our sines and cosines. And our SOHCAHTOA is over here. So we have everything we need to work with. We want the x direction here, x direction, and you can see that's the one that's adjacent to the angle. X direction is adjacent to the angle, so is adjacent cosine or sine. We see the A here for adjacent, and that's right next to the C for cosine. CAH, SOHCAHTOA. It's a little hard to see. Let's try it with this color. CAH. Carried away. Cosine, adjacent, hypotenuse. So cosine goes with adjacent. That's what we want. So the answer we're looking for there is cosine, and that's what this animation is going to walk us through there. I jumped the gun. I over animated, so you'll see adjacent goes with cosine, and that's what we wanted. So at least we agree with ourselves, but you can see there, adjacent is the x direction. That was the whole point of this, is why did we want x direction, or why do we want adjacent, why did we want cosine? It's because the problem is asking for that x direction accelerations. We need to get away from this 50 degrees. So far we've been working at that 50-degree angle. We just want the x direction. So this last part is just to take the force that we calculated at that 50-degree angle. Now we know we need cosine from that last portion of the problem. So we'll take that total force, multiply it by cosine, get our angled force, or excuse me, we want to get that x direction force. X direction is what we want. Once we have the x direction force, we can find the acceleration in the x direction through Newton's second law. So now, notice we want to use the mass of the spaceship, because that's what we want to calculate. We want to do our calculations here on the Star Destroyer, the spaceship. So we use the mass of the asteroid to figure out that total force through Newton's third law. So we figured out how much force was there between the asteroid and the spaceship. Once we got that force, we can then figure out the acceleration of the Star Destroyer. So now we're doing calculations on the Star Destroyer. We want to use the mass of the Star Destroyer. So there's our free body diagram from part 2. We know that the force from the asteroid at that angle, that 50-degree angle, is about 1.5 million newtons there, 1.49 million newtons. We want to multiply that by an angle of 50 degrees. I'm sorry, I forgot to move my degree symbol up to the subscript or superscript there, but that's okay. We need to multiply it by cosine of 50 degrees is what I'm trying to say there. So we plug in the force. We plug in cosine of 50 degrees. I just got that from Google. I Googled cosine of 50 degrees. It told it to me at some decimal, but it rounds to 0.643. And that gives us that our x direction force is 959,019 newtons. So that's our x direction force on the Star Destroyer. So we know force, we know mass, we can find acceleration. So F equals ma in the x direction. Plug in our force x and our mass, and divide to find acceleration in the x direction. So that's it. That's the answer there. All you needed to do really is take that angle and change it to the x direction. And how did we do that? We did that with cosine right here. We took the angle, we used the cosine of that angle to get the x portion of that. Why did we use cosine? Because the x portion is adjacent to the angle. So one more time, our angle kind of looks like this. That looks terrible. One more time. And if I can't do it better, wow, that was so much worse that I have to try a third time. Okay, one more time. Well, whatever, we'll roll with it. But there was our 50-degree angle right there. That angle, the x direction side of it right here was touching that angle. The y direction side on the other end here was not touching that angle. So because the x direction side was adjacent, that made it cosine, and therefore we did all of this to go from the angle to the x direction. Once we had the x direction, it's just F equals ma, just like we're used to from before. So that's it. I was going to have you guys watch the same video walkthrough for that really hard problem from the homework yesterday as well, but that seemed like way too much for one day. So we've watched this video today. Here's what I'd really like you guys to do to finish up the day today. Go ahead and finish yesterday's homework if you haven't already, including looking at that hard problem where Mr. Billman's dragging the box. At least look at it, set it up, and then if you get stuck from there, go ahead and turn it in right there, and that's fine. I'll send you the answer key to that, and then spend the rest of your physics time today studying the answer key to that, and see if that answers any of your questions. And then tomorrow, we can go through the video and the notes walking through how do we solve that really difficult problem dragging the box. Hopefully problems 1, 2, and 3 you guys were able to at least attempt. Hopefully this video maybe clears up some of those questions you may have about using sine and cosine. But if you haven't already finished that physics in 2D practice number 2, those 4 questions with dragging of boxes, pushing lawnmowers, I think there was a cannon firing in one of those questions, please get that done. Once you turn it in, I'll give you the answer key. You can study that answer key for the rest of your physics progress today. So yeah, get that homework turned in today so you get the answer key, and tomorrow we'll watch a walkthrough on how to solve those really hard problems. And have a good Tuesday.